Hey guys, Math 150, Monday, Wednesday. I'm recording this instead of doing it live, so you have something to watch. It's chapter 8, section 1 and section 2, and it's on radicals. And then after you're done with that's funny. After you're done watching this, then you can head over and meet Jan in the study session that she usually has. Okay, here we go. Take a look. So I'll be working right out of your packet like I typically do. And so if you turn in your packet on section 8, we'll get started on your introduction to radicals. There's a few things that hold you responsible for knowing. Some of the vocabulary. That symbol, which you probably recognize, is called a radical sign. And there's a little cusp right here. Right there, a little, looks like a check mark, a little cusp. Right there is a number. When you don't see it, it's the number 2. And then we'll call it the square root. So you don't have to write the 2 there. We usually don't. But there is an invisible 2. The number that's in a cusp is called the index. So just remember that. The index is the number in the cusp. Right here, the index is a 3. And the stuff underneath the radical sign is called the radicand. Radicand. And most of you are probably going to be familiar with most of these anyway, like the square root of 25, you would typically say 5. So square root of 25 would be 5. We got to make sure that the radicand number, the number underneath, is always positive, because if it's negative, then we got a problem. If you have a negative square root, I said it wrong. If you got square root of a negative 25, we got a problem. And we would say it's not real. That's the phrase you want to use, not real. If you got the square root, I'll zoom in so you can see this, of negative, there's the negative sign, 25, and hit enter, it's going to say not real. That's what you do. However, if I end up saying, or typing in square root of 25, calculator then will say it's 5, of course. Examples that you've seen before, root 1, of course, root 0 is 0, root 9 is 3, root 16 is 4. Now that negative on number 6, that negative on the outside is okay. It's just not on the inside. So this would be negative, square root of 100 is 10, so negative 10. Fractions as well. So you'd have 7 over 9. Square root of 8 is okay. Not negative. Square root of 8 is okay. It just doesn't have a nice answer, sometimes we call it. You're going to learn how to deal with this coming up. And of course, as I said, square root of negative radicand, you just don't know how to handle it. So sometimes we say undefine. It's better to say not real. That way you'll match at the back of the book and possibly in the multiple choice portion of your test. So in 8.2, see, that was 8.1, just an introduction. 8.2, excuse me, continues with dealing with radicals, but like the last problem where it has an 8, the last problem that had an 8, this one here, it's not a perfect square. I'll say it again. Perfect squares, but a different way. Perfect square, the 4 is a perfect squared number. 9 is a perfect squared number. And 25, 36, 100 is a perfect squared number. So what that means is 2 numbers are identical, 10 and 10. So you take the product, becomes a squared number. 100. 100 is a squared number. So when you come over here and you say, excuse me, like here, cube root of 6, I don't know. When I say cube root, you have to have three numbers. These same three numbers, when you multiply them together, it gives you 6. You just don't know what that is. Unlike here, the same three numbers, that gives you 8. And that would be written as, and I wrote that wrong. That was really weird. It's not 3 times 3 times 3. That, of course, is 27. It would be 2 times 2 times 2. Or the cube root, don't forget to put the little 3 in there, because if I didn't put the little 3 in the cusp, it would be interpreted as square root. So the cube root of 2 cubed, and if you can put it that way, the cube root and the cubes, these cancel each other, and you're just left with 2 the base. Now, previous section, you couldn't have negatives as part of the radicand for square roots. Anything that's an even index, even like 2, 4, 6, 8, the index is an even number. You can't have a negative radicand. But the odd is okay, because you can have an odd number of negative signs, and you're okay with that. So for instance, this is a triple, -2 raised to the 3rd power. See, this would be a cube root of -2 raised to the 3rd power. So the cube and the cube root cancel, and all you're left with is the parentheses, -2, or plain old -2. Cube root of 64 is a perfect cube. So if you're not quite sure, I wonder if it's, don't forget, it's not the square root. That would be square root of 64 is 8. This is the cube root. So you have to come up with 3 numbers that give you 64. 3 numbers that give you 64. Well, if you went 3 times 3 times 3, 3 numbers, but that doesn't give you 64. So how about 4 times 4 times 4? And, so there's your 64. Therefore, the cube root of 64 is the base 4. Another way of writing this again is the cube root of 4 3 times. And the cube and the cube root cancel, so then you're left with just 4. The 4th root of 1/16, well, how you get a half is the 4th root, and it turns out 1 is really nice, of course. You get 4 1s in there. And then 16 is 2 times 2 times 2 times 2, 4 of them. So that's why it comes out as a 1 and a 2, because you got 4 of them. The 5th root, remember the negatives are okay, just like here. The negative is okay as part of the radicand with odd indices. That's an odd number, and that's called an index. So you'll end up with a negative, and you just have to take your calculator, because I don't think I'd know that 243 is a perfect 5th power. Just start taking your calculator and say, I wonder if 243, I wonder if 5 3s, I wonder if 5 5s, any of those questions would give you the 243. And it turns out 5 3s does. Same thing with 32. 2 times 2 times 2 times 2 times 2. Try it, check it out, and you'll find that's 32. So again, if you did that, then you'd have the 5th root, 5th right here, and that would be the negative, but then you'd have 3 to the 5th over 2 to the 5th, and the 5th powers and the index being 5, 5 cancels each other, and so here you have a negative with a 3 over 2, which is exactly what you have right there. Now, with the variables, it gets a little peculiar. Here, I'm going to try something here for you. Square root of, let's say, 32. Now, 32 is not a perfect square. 36 is, but not 32. So if I did this, I went square root, and I know that 32, just from a previous problem, there's 5 2's that make up 32. 5 of them. Now, that's a perfect square. 2 times 2 is 4. I could rewrite this as the square root of 4. So right here, times the square root of 4, which is right there, times the square root of 2. So yes, you can bust up the square root of a product of numbers into the product of square roots. And this would give you 2 times 2 times, and this is a leftover, root 2, which then gives you, at the end, 4 root 2. Another way of looking at it is if I wrote this as 2 to the 5th power. Now watch this, watch what happens here. This would be the square root of 2 to the 5th power. 32 is 2 to the 5th. There's a little index of a 2 right here. I'll put it there for you. And if you did a little think bubble right here, and you take the power in the index, okay, the power is 5 and the index is 2. So if you took the power and divide it by the index, you get 2.5. 2 and a leftover. You knew that. 5 over 2 is the same as 2.5. The 2, the whole part, tells you how many 2's come out. I know a lot of 2's, I know. Look at how many 2's came out. There were 2 2's. Whole part tells you how many 2's come out. And the fractional part, the 1 over 2, says how many, 1, is left underneath. So there's 2 2's that came out, and there's 1 left over. I'll show you this much. There's a little 2 right here you don't see. Okay, so a to the 4th. 4 divided by 2 is 2. 2 divided by 2 is 1. The square root of a to the 4th is a squared. And the square root of b squared, so the index and the power, they're the same. They cancel, and you're left with b, or b to the 1st. This would be the simplified version of it. I know, kind of a little different with the variables. Let's try the next one. All right, so the cube root, it's okay to have negatives. It's all right, comes out as a negative. Cube root of 27 is 3. So there's your 3 sitting out there. The last part is you've got x to the 12th power. Now, that means you've got 12 x's. How many triples with 12 of them? You got 12 x's, and you group them in 3's. You've got 4 groupings. Or 12 divided by 3 is 4, and that's how you get your result right there. And then like manner, over here, the 5th power, the 5th root, 32 is that number that we've done before. There it is right there. So the 5th root of 32 is 2. So the 5th root of 32 in the denominator is a 2 in the denominator. And then the powers, you divide. So 10 divided by 5 is 2. 15 divided by 5 is 3. Your best looking answer looks like that. Now going back to square root of 81, we know that's 9. And what about these funny numbers? Like I did 32, square root of 32, not a perfect square. Now there's a way of simplifying it. Going back over here, square root of 32. 32 came out to be 4 root 2 at the end. That's the target number you're looking for in this section 8.2. So how I did this, 84, I broke it up into perfect squares. So instead of taking 84 and writing a bunch of numbers, prime numbers, I could have done that. I could have said, what goes into 84? 2, and just keep busting it up as prime factors, like that. And then you say, gosh, that can be going farther, like that. You could do that, and then you got a pair of 2's, but that's the same thing as 4. Square root of 4 is 2. The leftover is going to be 21 as a radicand. So the best answer, 2 root 21. Let's try a different one. Bust this up or find 2 numbers that give you 72. And maybe an idea, I want to target perfect squares. So instead of targeting 2, which is not a perfect square, target perfect squares like these guys. Will any of those numbers go into 72? Sometimes you don't know. You say, what if I took 72 and divide it by 25? And of course, you know that's not going to work. What if I took 72 and divide it by 16? No, not going to work. 4.5 is not good. So I took 72 and I divided that by, let's say, 9. That works. Or 72 divided by 4, and that works. So you could take them in pieces, which is what I did right here. I took the 4 times 18, and then there was a 9. So how about the product of those two? 9 and 4. Does 36 go into 72? That's what you would have tried. Even though up here I said, how about 4, 9, 20, and so on. It could have been 36 is the next one. So 72 divided by 36, and you find out 36 times 2. So if you can find the biggest perfect square, it just takes less time to simplify your answer. So at the end of this, you'd say square root of 72 is the same thing as the square root of 36 times the square root of 2. Square root of 36 is 6, and you leave the square root of 2. And this is your final result. Now let's do a few examples. 24, not a perfect square. 25 is, but not 24. So consider 2 numbers that give you 24. If you can't find the biggest perfect square, just go with anything that works, like 4, for instance. And if you have to do it a little bit further after that, simplify it, then you can do it again on the second go around. But square root of 4 is 2. So 2 root 6, best answer. Root 150. Okay, so you'd say, well, 2 goes on 150. 2 is not a perfect square. 2 is not a perfect square. So try to come up with perfect squares. 150. All right, well, let's see. What's the 4? 4 is a perfect square. So try 150 divided by 4 and see if you get something. Yeah, you don't. What's the next perfect square after 4? 9. Try 150 divided by 9. No. What's the next perfect square after 9? 25. I think we have a winner. 25 times 6. So then what you do is you go square root 25 times 6. Square root of 25 is 5, and you leave root 6 next to the 5. It's really 5 times root 6, but I'll leave it without the dot. 52. I know 2 goes into it. I'm looking for a perfect square. I know 2 goes into it. How about start with 4? 4. And 4 works. So let's do that. 4 times 13, square root of 4, square root of 13, 2 root 13. Next one. So 2 times, all right, two numbers, I think you know it. Two numbers that give you 99, 11 and 9, or 9 and 11. Square root of 9 is 3. So you put the 3 out here where the 2 is, leave the root 11. So your best answer, now you multiply the numbers that are outside, so your best answer is 6 root 11. Okay, now it comes the variables. Remember how that little trick that I had before? Shortcut, if you want to call it. You take the index and divide it into the power, or take the power divided by the index. This is the same, well, if you think of it this way, you go x to the 9 over 2, and 9 over 2, okay, what's the whole part? 4, it's 4.5. So that's x to the 4th with the leftover of 1. This is equal to x to the 4.5. So 4 and 1 is the leftover. So x to the 4th root x. So x to the 4th root x. Okay, this one. Same thing, the index is 2. So 20 divided by 2, nice. That's a 10, no leftovers. 2 divided by 2, looks like you're going to get x to the 10th and y to the 2nd. And no leftovers, so there's no extra radical hanging out. Okay, this one here, 96. I don't think 96 is a perfect square. And this is what you'd ask. I don't think 96 is a perfect square. I mean, you try it if you're not sure and you say, yeah, it's not. So I wonder if 96 is divisible by numbers like 4. We'll try 4. And it is. So you could work with the 4 and see what's left over, but notice the leftover, there's another 4 in there. So you could do this, which is not a problem. It's a square root of 4 times 24, and then x to the 4th. You could take this and make it into a 2, square root 24 x to the 4th. You could do that, that works, but you need to keep going. 24 has another perfect square of 4. So what do you do with the 2? You leave it out here. This 4 comes out. I'll even show you right here. This is 2 root 4 root 6 x to the 4th. That's 2 times 2. Okay, that's 4. X to the 4th. Square root of x to the 4th is x squared. And what's left over is a 6. This came out right here as x squared. Square root of x to the 4th is x squared. So the best looking answer is this right here. Okay, and the last problem looks like in this page, it looks like I get to bust this up into square root. Okay, 5 times 100, x to the 13th over y to the 22nd. Square root of a, okay, so this is going to be a fraction. Square root of 100 is 10. There's still a root 5. Still a root 5. Okay, so there's a little 2 right here. It's a square root. 13 goes in, or 2 goes into 13. Okay, how much whole? 6 times. 2 goes into 13 6 times. And there's a leftover of a 1. I'll do that again. 13 divided by 2 is x to the 6th, and there's a leftover of 1. And down here, 2 goes into 22 11 times, no leftovers. So the best looking answer looks like that. So it's not a long lecture. It's on 2 sections. Sounds like it's a lot. 8.2 has a little bit more meat to it, a little bit more substance. And you can always stop my recording, rewind it, go back and listen to it again, or use YouTube. You could use Just Math Tutoring, which I believe I've shown you. And if you've forgotten, you can go to your Canvas homepage for this class, go all the way down at the bottom, and you'll see this pair of glasses that says Just Math Tutoring. Follow the link, and you'll see that he's done a number of other similar examples in sections that is like 8.1 and 8.2 from our author. So that's in your Canvas homepage. Go towards the bottom, and click on the link, Just Math Tutoring, and check it out. Okay, that's it for now. You guys have a good rest of the day. Go see Jan. She'll be waiting for you. All right, take care.